Good afternoon, everyone. I hope everybody's doing fine today. For the next couple of weeks, we're going to be working with things that are called trigonometric identities and trigonometric proofs. And today's lesson is just a basic introduction to working with identities. This is lesson 30.04, and I believe this is on page 11 of your lesson handout. So I'm going to start off by explaining to you what an identity is and give you examples of things that are identities and examples of things that are not identities. First of all, an identity is an equation that has a certain property, and the property is the equation is always true. Now, in your note package, I'm saying it's always true for any allowable values of the variable. If there happen to be a non-permissible set of numbers that you are not allowed to use in the equation, so for example, if the equation has square roots and you're not allowed to put negative numbers in underneath the square roots, then we don't worry about that. What I'm saying is the equation is always true for any value of the variable that you are allowed to put in. And I want to point out something to you right now, that an identity is an equation that has a special property, but not all equations have that property. In other words, all identities are equations, but not every equation is an identity. So if you take a look at what we're viewing here, I have an equation that says 2x plus 3 quantity squared equals 8x squared plus 24x plus 18 over 2. And I'm telling you that that's an identity. What that means is that it doesn't matter what number I put in for x on the left and the right side, I'm going to get the same answer. The left and the right side will always be equal. Let me show that to you on my calculator. I'm going to put in for y1 the left-hand side of this equation. So in brackets, I have 2x plus 3, end brackets, and I'm squaring that. And I'm going to right now go to my table setup, and I'm going to start at 0 and go up by 1. And that means if I were to go to my table in the calculator automatically generates all of the values of that expression for different values of x. So when x is 0, the left-hand side is equal to 9. When x is -2, the left-hand side is equal to 1. When x is -4, the left-hand side is equal to 25. Well, now I'm going to go back to y, and for y2, I'm going to enter the right-hand side, which is in brackets on the top, 8x squared plus 24x plus 18, end brackets, and divide the whole thing by 2. And now if I go to my table, I notice something. I notice that y1 and y2 are always equal to the same thing. And I realize that my table is generated with integers. I'm using x equals 1 and 2 and 3, etc. I'll show you in a second that it works with decimals as well. But for example, when x is 4, y1 is 121 and y2 is 121. That means when x is 4, the left side and the right side are always equal. I could set up my table so that the independent variable, which is x, is selected to be asked for. And when I go to my table now, my table is blank. It's waiting for me to put in a number. And I can put in -3.58 if I want. And I see that the left and right sides are still equal. I could put in 3 pi if I wanted to, and I can see that the left and the right sides are still equal. So that equation listed first on this page is an identity. Now let's try the same thing with the second equation, where I have 4x minus 4. I'll put that in for y1, and it's equal to 5 multiplied by, in brackets, x plus 1. And I'm going to go to my table. And I discover that for different values of x, I get different values of y, which means, for example, I'll pick a simpler number to work with. When x is 5, the left side is equal to 16 and the right side is equal to 30. When x is 9, the left side is 32 and the right side is 50. So the left and the right sides are not always equal. If x is -9, however, they are equal. So there is a number that makes this second equation true, but not every number makes the second equation true. And it's for that reason that the first equation is an identity because it's always true, but the second equation is just merely an equation. It's not an identity. Now in trigonometry, there are a number of identities. You've already been introduced to 3 of those identities, and they are called the reciprocal identities. The cosecant of an angle is the same as 1 over the sine of the angle. What this means is that you can pick any angle you want, and if you figure out what 1 divided by sine of that angle is, and you also figure out what the cosecant of that angle is, you will get the same thing. In other words, this equation, cosecant of theta equals 1 over sine of theta, is an equation that's always true, which is why it's called an identity. Similarly, secant of theta is equal to cosine as a reciprocal is always true. Secant of theta is equal to 1 over cosine. Cotangent of theta is always equal to 1 over tangent. Now, I can't prove this to you on the calculator the way we did with the algebraic equations in the previous section because I don't have a secant button on my calculator. In order for me to put secant of theta into my calculator, I actually have to type 1 over cosine of theta. However, if you went online and you went to a website like Wolfram Alpha and you typed cosecant of a particular number, in fact, I'm not in any big rush here. Let's do that. Wolfram Alpha is a mathematical site that it's kind of a mathematical search engine, and anytime you enter anything in, it will trawl through the whole internet finding everything about it. So if I enter cosecant of, I'm going to pick an angle and I'm going to be in radian mode, that's what this website defaults to, negative 2.4 radians. And you can actually, it tells me right away what it's equal to. It doesn't even have to think about it. It says that the cosecant of negative 2.4 is negative 1.48047 something. Now, cosecant is the reciprocal of sine. So if I were to find 1 divided by the sine of negative 2.4, I should get the same thing. 1 divided by the sine of, I had negative 2.4 radians. So let's find out what Wolfram can tell me about the reciprocal of the sine of negative 2.4. It gives me the same number. The result is negative 1.48047, which is the same as the cosecant of negative 2.4, negative 1.48047. The lesson here is if you have a way to calculate cosecant and you have a way to calculate 1 over sine, you'll get the same number for every single angle. What I mean by that is each angle will give you the left and the right side being equal. Obviously, if we went back to Wolfram Alpha and I used a different angle, not negative 2.4, I would get a different result, but it would be the same on the left and the right side. So those are called the reciprocal trigonometric identities. There are more trigonometric identities. These are referred to as the quotient trigonometric identities because they are quotients. When you divide things, you are finding what's called a quotient. So for example, tangent of any angle is always equal to sine of the angle over cosine of the angle as long as the angle is allowed to be placed in here. If you were to try to find the tangent of 90 degrees, you would discover that it's not defined. And we talked about that when we learned about the unit circle. The reason it's not defined on the unit circle is because tangent is y divided by x. And at 90 degrees on the unit circle, x is 0. But that's not what's important today. What's important today is that the left side of this equation that I've highlighted is always equal to the right side. So for example, and I'm not going to go to my y's to do this, if I were to take the tangent, let's go in degree mode this time, just to show you that it doesn't matter. If I were to take the tangent of 85.23 degrees, I get a certain value. If I were to take the sine of 85.23 degrees divided by the cosine of 85.23 degrees, I get the same value. The left and the right side of this equation are always equal, which means that equation is an identity. And similarly, there's another quotient identity that says cotangent is equal to the cosine of the angle over the sine of the angle. Now, you are not going to have to memorize these. These are all on your formula sheet. And they would certainly be given to you if we had exams. There is a third set of identities, and these set of identities are called the Pythagorean identities. And they are called the Pythagorean identities because they are derived by using the Pythagorean theorem and the unit circle. But we don't need to worry about how they're derived in this course. What we need to worry about is that they are called Pythagorean identities, and what that means is they are always true. For example, if I were to pick an angle, and I'm going to focus on this identity, which is a very, very popular is the wrong word. You encounter this identity, sine squared plus cos squared equals 1, a lot of the time. You see it a lot. So from now on, when you see sine squared plus cos squared, or sine squared theta plus cos squared theta, I should probably say, we can always just say, you know what, that's 1. Let me repeat that and draw an analogy here. If you're working on some problem and a part of the problem has sine squared theta plus cos squared theta in it, then you can rewrite the problem, and instead of writing that sine squared theta plus cos squared theta, you can write 1. You can change it to the number 1. You can simplify it. It's very similar, and I'll get back to the identity aspect of this in a second. It's very similar to you having an expression, and there's all kinds of stuff everywhere in the expression, but somewhere in the expression is 2x plus 7x. Well, we don't continue to write 2x plus 7x as we progress through the problem. As soon as you see 2x plus 7x, your next step in the problem, and it doesn't matter what else is present, your next step in the problem is to write 9x in place of that. And you're going to really have to get used to doing that kind of thinking as we work through the next couple of weeks. You want to identify things that can be written in a simpler form. So, getting back to the identity, sine squared of an angle plus cos squared of an angle gives you 1. Don't forget that what sine squared means is it means sine of theta quantity squared. So that's what that identity means. Now, if I pick an angle, and we'll try it this time in radians, again, I'm just flipping back and forth here to show you that the identities work in either mode. I pick an angle of 1.4 radians. If I want to take the sine squared of 1.4, my calculator is smart enough that when I type that, it's going to square the whole thing. I don't need to put the sine of 1.4 in an additional set of brackets. Now, if you look at what that's equal to, it happens to be equal to this number. If we were to take a look at cos squared of 1.4, it happens to be equal to this number, but when you add them together, when we take sine squared of 1.4 plus cos squared of 1.4, You get 1. And it doesn't matter what angle you choose, you're always going to get 1. There are other trigonometric identities. You can recognize them because they all contain the number 1, and they all contain trigonometric ratios that are squared. So let's take a look at some strategies we're going to be using here. And I'm going to keep coming back to these strategies. And I think it's only fair to warn you that I have never met a student who understands this and gets really good at it on the first day of practicing it. Your goal is always going to be that every time you sit down and do more of these problems, it is a little bit easier than it was the last time you did it. This is something that takes a lot of getting used to. But here are the strategies I've come up with that I think will be able to help you. One of the strategies in solving problems that we're going to be working on is to write everything in terms of sines and cosines. I'm not saying that is always going to lead you to an answer, but a lot of the time it will. What the second point is saying is to keep an eye out for pieces of known identities. For example, I hope I've talked about sine squared of theta plus cos squared of theta enough that if you see that in the future, you go, oh, yeah, I recognize that. That's the number 1. One thing that's going to be useful from time to time to simplify the expressions in the problems we're going to be doing is to factor. Now, we're not going to be factoring x's and y's and z's and a's and b's. We're going to be factoring sine of thetas and cos of thetas and tan of thetas and secant of thetas, etc. The fourth point, just to make sure that you understand what it means, is if you're ever faced with a problem and in the problem you see fractions that are separate from one another, like sine of theta over tan of theta plus cos of theta over tan of theta, you should put them together because they have a common denominator. And if they don't have a common denominator, then convert them to a common denominator. In this case, what I'm saying is you would end up writing sine of theta plus cos of theta all over tan of theta. This would be the strategy that I'm suggesting here. And then the last point is just this idea that I came up with a number of years ago, because I watch students work on these problems, and there's a certain level of frustration that everybody encounters. And the suggestion I have is if you start doing stuff and you change the problem progressively to a different problem in the hopes of getting it closer to an answer, if you feel you're getting further away from the answer, if you feel things are becoming too messy and too cluttered and too confusing, then forget everything you did and go back to the beginning and start again and try something different. What's going to happen with some of you is you are going to be working on these problems and you're going to try one on your own and you're going to look at it and you're just going to sit there and stare at it because you don't know what to do. The analogy that I've been using for a number of years is that you're stranded in the middle of nowhere on a road. There's a road there, and it's dark, and there's a lot of bush, and you can't really see the daylight, and you know you want to get home. Well, if you just freeze and you just sit there and you don't do anything, you will never get home. What you need to do is start walking. You need to try something. And with math, it becomes even easier because you're not going to hurt yourself in math. So what I'm suggesting is you imagine that you're on this road and you start walking down the road. You start trying things. You take some steps. And hopefully the steps that you take mathematically result in the sun starting to come out a little bit more and things become a little bit clearer and you feel a little better. What the last point is saying is if you're walking down that road and things get darker and darker and you start hearing growls coming from the bush, then go back to the beginning and start again. Okay, With all that in mind, I know I probably haven't instilled a whole lot of confidence in you, but don't worry, everybody struggles with this to begin with. On your formula sheet, these are the identities and where they are in relation to each other. So there's the quotient identities, the reciprocal identities, the Pythagorean identities, and you can see above it our arc length formula, which we've already learned about. All right, let's take a look at some examples. You were asked to simplify tan squared of x multiplied by cos squared of x. So there is a way to simplify this. There's a way to write it in simpler form. The very first suggestion I have given you, everybody, is to write everything in terms of sine and cosine. Well, there is a quotient identity that says tangent of x equals sine of x over cosine of x. If I have tangent equals sine over cosine, then tan squared would be sine squared over cosine squared of x. And I'm multiplying that by cosine squared of x. I've talked about this in class numerous times, but I want to highlight it here. Look at how I wrote cos squared of x. I wrote it so that I can imagine or even write over 1. I don't think writing sine squared of x over cos squared of x multiplied by cos squared of x this way, I don't think that's useful visually. Because we can see here that what we are allowed to do on the left is we are allowed to cancel the cos squareds, and all we are left with is sine squared of x. Tan squared of x times cos squared of x is sine squared of x. We've simplified it. Number 1b, we want to simplify this. Well, we're going to write everything in terms of sine and cosine. So we have a large fraction, and on the top of the fraction we have cosecant of theta. Well, cosecant of theta is 1 over sine of theta. So I am going to replace the cosecant with 1 over sine of theta, multiplied by secant of theta is 1 over cosine of theta. How do I know these things? They're on my formula sheet. So I can replace secant with 1 over cosine of theta. Cotangent of theta, there's a quotient identity that says cotangent is cosine of theta over sine of theta. So on the bottom, I'm going to put cosine of theta over sine of theta. Now, this is what we refer to as a complex fraction. It is a large fraction. It is a large fraction. There is a numerator to it and there is a denominator to it, but when you look at the numerator contains fractions within it, and when you look at the denominator, so does the denominator. The simplest way for you to simplify a complex fraction is to multiply the numerator and denominator by whatever you need to eliminate all of the mini denominators. I do not want to have that sine of theta on the bottom of the top or the cosine of theta on the bottom of the top. So I'm going to multiply by sine of theta, cos of theta, and I need to do that to the top and to the bottom. And by the way, when I do that to the bottom, I'm going to end up canceling the sine of theta on the bottom of the bottom. So when I multiply sine of theta, cos of theta by 1 over sine and 1 over cos, a number of things happen. The sine of theta cancels with the sine of theta. The cos of theta cancels with the cos of theta, and I end up with 1 on the top. Everything cancels. I'm not left with nothing. I'm left with the number 1. And on the bottom, what cancels is the sine of theta, so I'm left with, on the bottom, cosine of theta multiplied by cosine of theta, which is cosine squared of theta, and that is an answer if we wanted to. Since cosine and secant are reciprocals of each other, I could write secant squared of theta, because secant is the reciprocal of cos, and cos is the reciprocal of secant. All right, let's take a look at C. We have cosecant squared of theta minus cotangent squared of theta. The thing that pops out here visually is that there are squareds involved. And I know that my Pythagorean identities have squares in them. So for example, when I look at the third identity, the one on the right, I can see that cosecant squared is exactly the same as 1 plus cotan squared. Right? It says cosecant squared and 1 plus cotan squared are the same. Well, what that means is that up here where I see a cosecant squared, I can put 1 plus cotan squared of theta. And that means this expression will become 1 plus cotan squared of theta minus cotan squared of theta. Well, cotan squared of theta minus cotan squared of theta is 0. So what this expression is equal to is 1. And by the way, just to let you know, sometimes you really struggle at these problems, and when you finally see it, it becomes obvious. You shouldn't feel bad about missing obvious points. This is very new to all of you. All right, we take a look at D. If you were to take a look at the list of suggestions that I gave you, there are 2 suggestions in that list that we would use here. One of the suggestions is to factor if possible. And the top has sine of x as a common factor. There's a sine of x in this term and in this term, so I can factor a sine of x out. When I factor sine of x out of sine of x, I'm left with 1, minus when I factor sine of x out of sine of x cos squared of x, I'm left with cosine squared of x. On the bottom, I have tan of x. Another item in the list that I suggested is to rewrite things in terms of sine and cosine. And tangent is sine of x over cosine of x. Now, we'll come back to that in a second, but I had told you a little while ago that you should be on the lookout for sine squared of x plus cos squared of x, because that is equal to 1. However, I want you to notice that if we were to subtract cos squared from both sides of this, if I were to subtract cosine squared of x from the left and from the right side, then what I would end up getting would be sine squared of x equals 1 minus cos squared of x. And incidentally, if you were, instead of to subtract cos squared from both sides, subtract sine squared, you would arrive at this statement. So I have told you that you need to keep your eyes peeled for sine squared of x plus cos squared of x, for the simple fact that it can be written as the number 1, because that's what it's equal to. But I'm telling you now that you should keep your eyes on the lookout for 1 minus cos squared, because it can be written as sine squared. Sine squared is simpler than 1 minus cos squared. Similarly, be on the lookout for 1 minus sine squared, because instead of writing 1 minus sine squared, you can write cos squared. When you take a look at where we're at in our work on the left-hand side of the page, we have 1 minus cos squared right here. Well, 1 minus cos squared is sine squared. So we can replace that with sine squared and get sine of x then multiplied by the sine squared of x, which was 1 minus cos squared, over sine of x over cosine of x. And we have that complex fraction structure that I talked about earlier. In order for you to eliminate that denominator of cosine of x that's on the bottom, you need to multiply the bottom of this expression and the top of this expression by cosine of x. What happens here is the cosine of x on the bottom cancels with the cosine of x on the bottom of the bottom. And now what we are left with is sine of x, sine squared of x, and cos of x on the top. But we have a sine of x on the bottom, so that can cancel with the sine of x on the top. And what we're left with is the answer. The answer is sine squared of x cosine of x. All right, and then we have the last example, which is also letter D. If you go through the list of suggestions that I've given you, the first one is to write everything in terms of sine and cosine, but that's a dead end here because it's already in terms of sine and cosine. I believe the second thing that I suggested to you was just a general suggestion to keep your eyes open for pieces of known identities. And I don't recognize anything here that's standing out. I don't see a sine squared plus cos squared or anything like that. Another suggestion I gave you was to factor, if at all possible, and there's nothing to factor. The last suggestion on the list said, if you've done some work and it's not going your way, go back to the beginning. Well, we haven't done any work. We're at the beginning. So the only thing left to do is to add fractions together. Now I'm going to rewrite the expression to begin with, and I'm going to space things out, and you'll see why in a little bit. So I'm taking sine of x over 1 plus cos x, and I'm adding cos of x over sine of x. Now I want to put these together with a common denominator. So what's the common denominator going to be? Well, this is very similar to me giving you fractions like 1/3 plus 2/5. If you added 1/3 plus 2/5, the lowest common denominator would be 3 multiplied by 5. And I'm not going to go through and add these fractions together. I just want to make the point that if your denominators were 3 and 5, the common denominator would be the product of them. The common denominator is not always the product of the two denominators, but it will be if the two denominators have no common factors. And 3 and 5 do not share any common factors, so that's why we need to multiply them together. When we take a look at the old denominators that we had in this expression, we have sine of x, and we have 1 plus cos of x. And there's nothing that we can factor out of those, so they don't have any common factors. The only factor of sine of x is sine of x. The only factor of 1 plus cos of x is 1 plus cos of x. So the common denominator is going to be the product of those two factors, just like it would be if the denominators were 3 and 5. So I'm going to rewrite both of these with a denominator of the product 1 plus cos of x times sine of x. And that's going to be the denominator for both of these, 1 plus cosine of x multiplied by sine of x. Now the reason why I rewrote the question and spread things out is I want to impress on you that when you are adding fractions, the whole goal is to convert the original fractions to fractions with the new denominator. When I look at the new denominator has a 1 plus cosine of x on the bottom and a sine of x. And that means that this first fraction, I need to multiply the bottom by sine of x to get that common denominator. But I can't just multiply the bottom of the fraction by sine of x. I need to as well multiply the top of the fraction by sine of x. When I take a look at the second fraction already has a sine of x in the denominator. What's missing in the second fraction is I need a 1 plus cosine of x. And I hope everybody appreciates that the order in which I write those two factors in the denominator doesn't matter. Sine of x times 1 plus cos of x is the same as 1 plus cos of x times sine of x. So what do I get on the top of my first fraction? Well, I need to multiply these two things together. That's what I'm going to get on the top. On the top of the second fraction, I need to multiply these two things together, which means I'm going to multiply the cos x times the 1 and the cos x times the cos x. Okay, what do we get on the top of the first fraction? Well, sine of x times sine of x is sine squared of x. What do I get on the top or the numerator of the second fraction? Cosine of x times 1 is cosine of x, plus cosine of x times cosine of x is cosine squared of x. And now I can put them together. And again, I don't want to spend a lot of time teaching you remedial fraction work, but if I had a fraction that was, say, 3 over 5 plus 17 over 5, I tell students at earlier grades to not think of it as 3 over 5, but to think of it as 3/5. And the reason is, if I add 3/5 to 17/5, it's easy for me to explain what's going on. I would just tell the students, if I had 3 kittens and I was adding 17 kittens, I would get 20 kittens and a whole bunch of happiness. But the point is, when you add fifths to fifths, they remain fifths, and you simply add the numerator. When you add the numerators together, you get 20 over 5, and I've chosen these numbers for a particular reason. 20 over 5 can be simplified because there's a factor of 5 on the top and a factor of 5 on the bottom, so it gives us 4. Okay, let's keep that in mind as we put these fractions together. Now we can put them together with the denominator of 1 plus cosine of x multiplied by sine of x, and we're not going to multiply that through. The hope, everybody, is that when we simplify the top will contain a factor that's included in the bottom, and we can cancel. So what do we get on the top? We get sine squared of x plus cosine of x plus cosine squared of x. And if I were in a classroom right now in front of a group of students, what I would say is the following. I would say, so the answer is 1 over sine of x. And what I would be greeted with when I told people that is a whole bunch of stares. And I would stand there and I would wait. And sooner or later, 1 or 2 students would start to nod and go, oh yeah, it is 1 over sine of x. And I would say to the class, everybody think about that for a second. Just take a look at the top and what's contained on the top and see if you can figure out why it becomes 1 over sine of x. And I would like you to pause the video right now, and I really, really want you to pause the video. I have a feeling when I say pause the video, a lot of the time you don't. I want you to pause the video, and I want you to eyeball this. And eyeball this. And see if you can figure out how I'm going from that first eyeballing expression to the answer of 1 over sine of x. When you've given it a good effort and you've thought about it for 2 or 3 minutes, Hopefully you figured it out. If not, you can unpause the video when you're ready and I will explain. Okay, so how do I do that? Well, on the top of this expression is sine squared of x plus cos of x plus cos squared of x. Now I can rewrite the order of those to sine squared of x plus cos squared of x plus cos of x. And on the bottom, I have 1 plus cos of x multiplied by sine of x. Hopefully, you recognize something in the numerator. There is a sine squared of x plus cos squared of x, which is equal to 1. That's that Pythagorean identity. And now what we have in the numerator is 1 plus that cos of x, which is still there. This cos of x right here, I have 1 plus cosine of x, and it's over 1 plus cosine of x times sine of x, and we have a factor of 1 plus cosine of x in the numerator and in the denominator, so they cancel, and I'm left with 1 over sine of x. There are a whole bunch of problems on the following 2 or 3 pages. And what I want you to do is I want you to try these. And try is the key word. At earlier levels in math, your teachers are always hounding you, well, you got to try, you got to try. What does that mean here? It means you have to start looking at your identities on your formula sheet and trying different substitutions and trying to factor and trying to write everything in terms of sine and cosine. You are going to struggle with this initially, but, and I'm speaking from experience, the harder you work at it, the easier it will become and the better you will feel about it. So as I say, give it your best shot. I do not know if I'm going to have time to post video solutions for this section. I'm really, really swamped right now. I will see if I can find time, but I may not. Don't forget, tomorrow I am in the Google Hangout during period 3. So if you need help, and I suspect many of you will, please stop by and I would be very happy to help you out. I hope you have a great rest of the day. Good luck with this stuff, and I will talk to you later.